Today our topic is alkyl halides, and we are going to study reactions of alkyl halide. If we talk about reactions of alkyl halide, then these alkyl halides, which are also called haloalkanes or halogenoalkanes, their reactions can be classified into following three categories. See one by one, and these are nucleophilic substitution reactions, organometallic reactions, and elimination reactions. So first of all, we see the nucleophilic substitution reactions. Nucleophilic substitution reactions are symbolized as SN. This N is just like the subscript. These are the organic reactions in which a strong nucleophile displaces the weak nucleophile, that is halogen in case of alkyl halide, from an electrophilic carbon. So now we should introduce two terms, nucleophile and electrophile. So first we will see what are nucleophile. Nucleophiles are the reagents which can donate an electron pair in a reaction. These are the electron-rich species. A nucleophile more often symbolized as Nu. This shows the lone pair, and U is symbolized for it is a symbol for nucleophile. So where does it attacks? Now see, the site of attack for a nucleophile, as nucleophile is electron rich, therefore it attacks on the region of the low electron density, means the positive center, that is the partial positive carbon in these cases that we are going to discuss, in the substrate molecule. Substrate molecule means where it is going to attack. So the target molecule in our today's lecture is alkyl halide. So the electrophilic carbon of the alkyl halide is the target carbon atom, which has the low electron density due to the high electronegativity of the carbon. So the bond between halogen and the carbon is polar bond, and where halogen is partial negative and carbon is partial positive. So the electrophilic center is the carbon where halogen is uh, bonded. And remember that nucleophile are negative or the neutral molecule with electron rich center. If you want to see, then you know ammonia is the neutral molecule, but it acts as a nucleophile because it has a lone pair. Similarly, hydroxide is a nucleophile, although it has a negative charge, and it also has lone pair. And similarly, water itself may act as nucleophile in several reactions. So a nucleophile can be a negative species, for example, hydroxide, cyanidine, or it can be neutral species just like water and ammonia. Okay, a general reaction can be represented by this method. R is any alkyl group. It is sp3 hybrid carbon, and there is a halogen. We can represent halogen by the letter X, and here we can represent a nucleophile, and the general representation of nucleophile is Nu and this lone pair. So what happens? This nucleophile, first we see that this bond between carbon and halogen is polar bond, where halogen being electronegative, it is partial negative, and carbon is partial positive. So this is the electrophilic center that is electron deficient due to the high electronegativity of the halogen atom. So the nucleophile attack on this electrophilic carbon atom. And if it is a powerful electrophile, sorry, if it is a powerful nucleophile, then it can displace halogen from here. So this attacking nucleophile displaces the halide ions that we can write now in this way. So H is here, R is here, another H is here, and we can use this Nu symbol for the coming nucleophile or the attacking nucleophile, while halide is separated as negative ion, and this is the leaving nucleophile. So this Nu is the attacking nucleophile, attacking nucleophile, and this is the leaving nucleophile. And this is our substituted product. So it depends whatever the nucleophile is there. Okay. Now another thing that the bond between carbon and halogen depends on the halogen atom. So the carbon halogen bond in case of chlorine, in case of bromine, in case of iodine is not of similar strength. It is not of similar strength. Strength is different. As we know, the size of the halogen atom increases down the group. So the distance between the nuclei increases and the electronegativity also decreases down the group. So the bond between carbon and iodine is weaker as compared to carbon and bromine, and it is weaker than the carbon and chlorine bond. So this bond can be broken easily as compared to C and Br bond, and C and Br bond can be broken easily as compared to CCl bond. So if we talk about the bond strength, so bond strength decreases down the group. We have seen that the bond strength decreases down the group. So the reactivity of alkyl halides increases down the group. So the carbon, as the carbon iodine bond is broken easily, so it undergoes SN1 reaction easily. Not SN1, any type of nucleophilic substitution reaction easily as compared to carbon alkyl bromides, and alkyl bromides can be can undergo easily in SN reactions as compared to alkyl chlorides. Alkyl halides can undergo several nucleophilic substitution reaction, and we start from here that alkyl halide, this is an alkyl halide that we have represented by Rx. This halide can be replaced by OH by using potassium hydroxide in aqueous medium or sodium hydroxide in aqueous medium, and ultimately it generates an alcohol. An alkyl halide can also undergo substitution reaction, nucleophilic substitution reaction, to give an ester when a sodium salt of carboxylic acid is used. It can also undergo nucleophilic substitution reaction with thiol group, and ultimately it gives alkane thiols. Generally we can say thiol. And the reagent is with SH group of alkali metals. Similarly, using potassium cyanide or sodium cyanide, we can convert alkane into alkyl halide into nitriles. So the general name for CN group is nitrile. And similarly, we can produce amines either by using ammonia gas. Ammonia can displace halide from the alkyl halide and produces alkanamines. Alkanamines. And alkanamines can also be produced by using these inorganic amide. This NH2 minus group is also known as amide. So it is also an alkanamine. And ethers can also be synthesized if we use alkoxides of alkali metals. Then it produces their respective ethers. We will see the mechanism of nucleophilic substitution reactions, which are symbolized as SN. The nucleophilic substitution reactions may proceed by two different mechanisms. The first is the SN1 mechanism, that's also called unimolecular nucleophilic substitution reaction mechanism. Another one is SN2. SN2 mechanism, these two refer to the bimolecular nucleophilic substitution reaction. Now we will see in detail one by one. Now, SN1 mechanism, that is the unimolecular nucleophilic substitution reaction. That is, in these reactions, the rate of reaction depends on the concentration of only one substance, and that substrate is the alkyl halide. The general mechanism follows following steps. It happens in tertiary alkyl halide due to bulky size of the alkyl radical. If the alkyl groups are bulky, then they prefer the SN1 mechanism. This bulky size causes steric hindrance, and the attack of nucleophile on crowded tertiary carbon is very difficult. Hence, one-step mechanism is not possible. Thus, the reaction proceeds in two steps because here halogen is more electronegative and ionizes easily. It comprises two steps, as we have discussed that it is a two-step mechanism. So in first step, ionization occurs and the carbon-halogen bond is broken. And we can see here that this bond is broken heterolytically. Heterolytic cleavage means that the whole bond is shifted on the halide. As a result, what happens? Halide gets negative ion, halogen gets the negative charge on it, and the carbon become deficient of electron because of the loss of one electron from here. So this carbocation is formed. And this carbocation, in case of tertiary alkyl halide, is stabilized by these alkyl groups because alkyl groups have electron donating effect. Next is the attack of the nucleophile. Now, this is the carbocation, and this carbon, this one, this carbon is sp2 hybrid. This carbon is sp2 hybrid, and here it was sp3. So the hybridization changes, and if it is sp2 hybrid, then remember that it is a trigonal planar structure. Now nucleophile can attack from either side of the molecule, this carbocation, either side of this carbocation. So on attacking the nucleophile on the carbocation, this electrophilic positive carbon, the new bond is formed between the nucleophile and this carbon, and again it becomes sp3 hybrid. And remember that the first step is the silo step, and it is a reversible step. I should write the reversible arrow here, and this is the silo step. And this is the fast step. So the silo step is always the rate determining step. And in this rate determining step, only alkyl halide is there. So that's why this reaction is, this mechanism is termed as unimolecular, because in rate determining step, only one species is present. So this is the kinetics of the reaction that you can see here. The rate is directly proportional to the concentration of alkyl halide only. No nucleophile is here. So when we remove the sign of proportionality, a rate constant comes over there. So this is the rate law for this such SN1 reactions. Now see the energy profile diagram. On y-axis, the potential energy is given, and here the progress of reaction is shown. What happens here? See. Now see here. This is the alkyl halide here. So it has the certain potential energy, and then it undergoes breaking of this bond. So the carbon halogen bond is being broken, and when it is broken, then a carbocation intermediate is formed, and this carbocation intermediate then interact with a nucleophile, and nucleophile approaches the carbon and it is forming the bond, and finally a nucleophile and carbon bond is formed. And again, I will I will emphasize here that it is the sp2 carbon, so it is trigonal planar structure, so nucleophile can attack from both the sides. And one more thing, that this carbocation is an intermediate. What is an intermediate? Intermediate are the species during the mechanism of reaction. Their presence can be uh, their presence can be detected by certain spectroscopic techniques during the reaction, but they cannot be isolated from reaction mixture. So an intermediate carbocation is formed during the mechanism, that is nucleophilic unimolecular nucleophilic substitution reaction. Now see some characteristics of this reaction that we have already seen. It is a two-step reaction. The reaction does not involve the formation of transition complex. Although there are two transition complexes, but these are not the transition complex that we will see in SN2 mechanism, that is the bimolecular mechanism, nucleophilic substitution, bimolecular reactions. So we will see over there. Here, what we are saying that an intermediate is formed. So it occurs through the ionization. So ionization involved that produces an intermediate. And the rate of reaction depends only upon the molar concentration of alkyl halide that we have already discussed. So these are the main features of the SN1 mechanism. Now, what are the favorable conditions for SN1 mechanism? The favorable condition is the presence of polar protic solvent. A polar protic solvent means a solvent that can provide a proton. For example, water. Water can provide a proton. Alcohol can also provide protons. So the polar protic solvent favor this reaction because they help in ionization in the first step. The presence of bulky alkyl groups also favor SN1 mechanism because these bulky groups prevent the attack of nucleophile from backside of the halide. And it also, if the carbocation has greater stability, it also favor the SN1 mechanism. And the stability of carbocation is here that the tertiary carbocation, that is also called 3-degree carbocation, is more stable than 2-degree carbocation. 2-degree carbocation is more stable than the primary carbocation, and primary carbocation are more stable than the methyl carbocation. Some authors consider methyl as the primary carbocation, and that's not wrong. It is also correct. But what are the primary carbocations? Primary carbocations are those which have only one beta carbon. What is the beta carbon? Actually, where the functional group is functional group is bonded, that carbon atom is called alpha carbon. So this is the alpha carbon, and it has only one beta carbon. So it is called primary alkyl halide. And if there are two beta carbon atoms in an alkyl halide, for example, you can see here. So this is the secondary alkyl halide. It has two alkyl groups. And this is the tertiary alkyl halide if there are three beta carbon atoms. So 1, 2, and 3. So this is the tertiary alkyl halide. This carbon atom is 3-degree carbon atom because it has 3 beta carbon, or it is further bonded with 3 other carbon atoms. So if we talk about the carbocation, then we should write here the positive charge. So these primary, secondary, and tertiary alkyl halide becomes the primary, secondary, and tertiary carbocations. So tertiary carbocations favor the SN1 mechanism, although the secondary carbocation can also undergo SN1 mechanism if other conditions are favorable. But it is difficult for primary alkyl halide and methyl halides to undergo such SN1 mechanism because of instability of carbocation as well as the attack of the nucleophile from backside is possible, from the opposite side of the halogen is possible. Okay, now we will see the reaction mechanism for SN2 reactions. So as we have already discussed that SN2, 2 stands for bimolecular. So these are the bimolecular nucleophilic substitution reactions. That is, in these reactions, the rate of reaction depends on the concentration of two reactants, that is alkyl halide and a nucleophile. Definitely, the nucleophile is the attacking nucleophile. The general mechanism involves the carbon nucleophile bond is formed. So the simultaneous formation of carbon nucleophile bond and the cleavage of carbon halogen bond is the main feature of this reaction, this mechanism. Since the attacking nucleophile enters as halide leaves, it attacks the carbon from the side opposite to that from which halide is leaving. So if we focus here, then we can understand that the primary alkyl halide are favorable for such mechanism. So preferably they follow the SN2 mechanism because in primary alkyl halide there is only one alkyl group and other two are the carbon hydrogen atoms on the alpha carbon where halogen is bonded. Now you can see here, as it is a primary alkyl halide, so you can see there are two hydrogen atoms here which are very small in size. So the attack of the nucleophile from the backside is possible. Now so you can see this is the general representation of the nucleophile, and this nucleophile can attack from the backside. And as a result, what happens? See, a pentavalent carbon is formed. Here, it shows the pentavalency of the carbon, although these are not the true bonds. But this is the pentacoordinated carbon. It has coordination from 5 sides. And this carbon atom is sp2 carbon. Remember that in this it is also sp2 carbon. It has been proven in different techniques. And this is called the transition state because one bond is being formed and another bond is being broken. The nucleophile and carbon bond is being formed while the carbon and halide halogen bond is being broken. This is called the transition state. And then what happens? When it completely enters the orbital, then halide has to leave, but it depends the strength of the nucleophile. A strong nucleophile is needed for SN2 mechanism. So ultimately it has to leave. So halide will leave from here and a new bond is formed between nucleophile and the carbon. And this is the leaving group, halide leaving group. Another important feature of this reaction is that it, it reverses the geometry of the molecule. And when we will discuss the chirality of molecule, then we can understand it in a better way. So the stereochemistry of the molecule changes if this carbon atom is the chiral one. So anyhow, this is the stepwise mechanism through the transition state for SN2 reactions. Now see the kinetics of this reaction. The rate of the reaction depends on both alkyl halide and the nucleophile. So this is the bimolecular reaction. And when we remove the sign of proportionality, so rate constant comes here. So this is the rate law. And in this rate equation, you can see two types of the molecule, two molecules are present. That's why this is called bimolecular nucleophilic substitution reaction. Now see the energy profile diagram. There is no intermediate. So there is only one hump. While previously you have seen in SN1 mechanism, there were two humps. One was there and one was there. And there were two transition conditions when the bond was broken and when the bond was formed. So there was an intermediate in SN1 mechanism, but in SN2 mechanism, there is no intermediate, therefore only one hump is there. So this is the energy coordinate, potential energy on y-axis and progress of the reaction on x-axis. So the potential energy of reactants are shown here. And now see, this is the transition state. This bond is being broken while this bond is being formed. So the energy of the energy increases for this transition state. And ultimately, as it is the strong nucleophile, so it has to leave. So halide left from the molecule and a new bond is formed between nucleophile and the carbon. And again, I will tell you again that the pentacoordinate carbon is sp2 hybrid. Now see the characteristics of the SN2 mechanism that we have already discussed, that it is one-step reaction because no intermediate is formed. So we will consider it one-step mechanism. Reaction involves the formation of transition complex because of the simultaneous bond breaking and bond formation. As you can see here, bond formation and here the bond breaking. No intermediate is formed, we have already discussed. It does not involve ionization. Definitely, if intermediate is not formed, so ionization is also not involved. And the rate of reaction depends upon the molar concentration, not only. It is my mistake. So rate of the reaction depends upon the molar concentration of both alkyl halide and the nucleophile. The favorable conditions for such mechanism is opposite to the SN1. In SN1 mechanism, we have seen that polar protic solvent is required, but here polar aprotic solvent is required. Remember that because alkyl halides are polar, so the solvent should be polar. But there are two types of polar solvents, whether the polar protic solvent, which can donate a proton to facilitate the ionization. But here acetone and acetonitrile or any other example, for example, DMSO. What is DMSO? See, dimethyl dimethyl sulfoxide is called DMSO. DMSO. It is also a very good solvent for SN2 reaction mechanism. So D stands for dimethyl M stands for methyl, S stands for sulf, O for oxide. So this is the sulfoxide along with the two methyl group. Uh, its structure is somehow similar to the acetone. This is the structure of acetone. So acetone and dimethyl sulfoxides are somehow similar in structure, but it is more polar as compared to acetone. So depending on the type of alkyl halide, we choose any of these solvent. So aprotic polar solvent, for example, acetone, acetonitrile, or dimethyl sulfoxide, favor this reaction as ionization does not take place. Presence of a small alkyl group favor this reaction because if there would be the bulky groups, then the attack of the nucleophile from backside would not possible. The presence of a strong attacking nucleophile as it displaces the leaving group more easily. So our nucleophile should be a stronger one that can cause ease to the breaking of the carbon and halogen bond. Less stability of carbocation. Definitely the primary carbocation is less stable. So methyl and primary carbocation easily undergoes SN2 mechanism. That's all. So that's all for these reaction mechanism.